So hi, my name is Rafal, and I have a problem. It's a machine tool problem, unfortunately. And so I picked up a surface grinder a while ago and decided to add some bits and pieces to it. So let's go through my project. So as you know, there's various different tools that you can buy on the market. Sometimes you can make specialized tools. You've got milling machines, which cut out subtractive manufacturing. So they cut out of 2D or 3D shapes out of metal, plastic, whatever you really want to use. You've got lathes, which turn cylindrical objects into other cylindrical objects, usually around a reference center line. 3D printers, I'm sure most of you are familiar with, just add material onto plastic usually, sometimes metal. See here, yeah. And so what else? Well, if you really want precision, and specifically precision with flatness, very good surface finish for sliding fits for different parts, you kind of want a surface grinder. There's my little surface grinder there. So surface grinder uses an abrasive wheel to flatten parts, usually steel. You can do aluminium as well. It can work on hardened parts, so parts that have been heat treated. And it does a really good job at maintaining very fine surfaces, and so you can do surface finishes as well as making sure that everything's the same sort of level and flatness. And usually these machines sort of work down to about the 1 micron, 2 micron level, especially for high-end machines. Mine is a bit of a cobbled together piece that I purchased, which is why it was quite cheap. It was made by a tool maker apparently quite a few years ago. So it's got some character, that's for sure. So milling machine, of course, you want to automate everything, control everything electronically. So I've done CNC conversion. The lathe, again, you want to automate everything. And yeah, CNC conversion. 3D printer, unfortunately, it already came with CNC, so no conversion there. All right, the anatomy of the surface grinder. So we'll go through just what the different parts are, and I won't use specific terms like X, Y, and Z. There's definitely some contention about which one's the Z axis, at least for me. All right, so you've got the spindle on the right here, which is what the arbor sits on with the abrasive wheel. You have a table that moves this way, and that's basically on a very loose chain drive, so you can do very fast passes. You then have a hand wheel, that feed hand wheel down here, which provides you with your travel left and right, and a cross-feed hand wheel for providing forward and back. On top of that, most parts are held on using a magnetic vise, which is that in the middle. That basically has a permanent magnet inside that you use a cam to put into position, and then it magnetically locks down to parts. So it needs to be like a steel part, for example. And of course, we have the vertical axis, which there was a handle there, but spoilers, there's now a stepper motor. So the hand wheel moves the head up and down, and that's where you do all of your precise steps to the height of the part. So your wheel goes along the top of the part and sort of abrades off a very small amount of the part. So really, you want the highest amount of precision in your measurements and your control over the whole system to be in that axis. Okay, problem set. Basically, it's about ergonomics. So you have to reach all the way over the surface grinder to get to this hand wheel. It's quite hard to move it because it was quite small, about that big in the end. Yeah, so it was a lot of effort. There's also a couple other things playing into it. You've got backlash in the system. Backlash is when you've got mechanical play within sort of some mechanical parts. That means that when you turn so you're turning, for example, the hand wheel in one direction and the surface grinder is going, the head's going down. If you turn to go the other direction, there's some slop in that interface, and you have to take up that slop before you can keep going. Now, on a very high precision machine, it's very difficult to adjust that manually, especially when you have to take a surface, a cut, and determine, how deep that cut was. And you end up doing what I did very frequently, which is running the wheel into the part and then seeing that you've just taken it off 0.5 millimeter. Probably a bit too much, and usually burning the part, then you have to go and spend half an hour getting rid of all the burn marks and whatnot. So that was the main reason for doing this this particular project, which of course is essentially a CNC conversion. So what are the options? I've done Linux CNC conversions before. It's good fun. It's interesting. It's expensive. It uses. I've used Raspberry Pis in the past. It's quite a good platform. But you have to interface with the hardware. There are some onboard I/O options for the Raspberry Pi, but realistically, I want to stay away from that for this project. Plus, you get to use MicroPython. So I wanted to create something that was specific to the use case here, rather than something that was very generic. One thing when you're running Linux CNC quite a lot is you have to use CAM software to create G-code, which you then have to run on the machine. So you have to know the dimensions of your part. But part of the fun of using manual machines is being able to just do things on the fly. So I wanted to sort of retain that. Yeah, so I chose MicroPython in the end. Okay, this is the hardware that I used. You've got an RP2040 in the Raspberry Pi Pico package. You have a glass scale, which is a linear scale where the head moves along. And that is a commercial off-the-shelf part, which gives you about a 5-micron resolution. So pretty good. Definitely can get better, but it gets a little pricey. I also had one of these HD 48 something displays just lying about from about 10 years ago. And so I decided to use one. And I had one of these keypads, so why not chuck that in the mix? All right, constraints, or more likely restraints. So requirements for the project, I could go on and make this whole thing automated. Every axis moves and it creates a perfect part, but then I'd be just making a CNC machine. So instead, I said for this part of the project, I wanted a few simple things. Display the current position on the LCD, reset a counter to 0. So because you don't have any homing in the system, you don't necessarily know where the part is. All you really want to do is know the current level of the part and then how far down you've traveled in a very precise manner. And what you can do at that point, you can just use conventional techniques for measuring your part and then zero off from there. So I want to control the up-down movement based on key input and also based on numerical entry. And on to the MicroPython finally. So I started looking at PIO and the RP2040 PIO is good fun. I've written some custom stuff for it, but it takes a while for you to get back into the swing of things and get a working solution. At least it does for me. So I had a bit of a look around on the web, and Peter Hinch has a great encoder RP2 file, which worked out of the box. It's written for RP2040, the user's PIO, and you can get the current value of the quadrature input, which comes into the micro. And I probably should have put a slide about that, but yeah. So it's just a digital format signal that tells you the step count that has changed and the direction. So you've got an A and B signal, and that tells you if you've gone a step in one direction and whether or not that step was positive or negative. So that library there did a great job of just basically straight away giving me a position value. Another library for the LCD. Now I'm using a very old LCD, like I said, from 10 years ago. Everyone now is concerned about I/O usage. So there's these modules that they tack on this I/O expander, I2C I/O expander. And so a lot of libraries out there which essentially give you this functionality over I2C. But I needed a parallel interface, ideally 4-bit. Didn't really want to go for the 8-bit with 12 control lines. That's quite a lot of I/O. So what I did, I found this one by Thomas Counts, which was very good. It actually split everything out into separate files and separate sections and classes. And it had a specific I2C driver that it created implementation of. And I basically took that file and replaced all of the I2C writes, which just toggle bits on and off, with I/O outputs. So all your signal lines and your 4 data bit lines. And it basically worked out of the box. It was just nice to have something working. So within half an hour, put some hardware together, slap some code together, and it works. But I guess the next stage or point was to get the stepper motor moving the axis. So I've got feedback. I know where the axis is, but I can't move the motor. I was doing this very late, but very quickly on Monday night, and it was very much a use the REPL, jump in, load all the modules in, test the commands, for example, the step and direction commands for the step motor, confirm the feature works, and then chuck all those parts into file. I did that for all of the interfaces, essentially. So very quickly, I had a working system. I'll go into some small issues I had a bit later on, stuff that I tried but didn't work in the very short amount of time that I gave myself. But for the moment, let's have a look at some results. And will this video play is the question. Okay, so you can see that there it's moving up 700 microns, and it's going up to 1500 microns. And that's because I'm actually, that's the automated system that's moving the motor up and down. And I haven't, I've started putting in some async I/O, but I'm moving the stepper motor sort of inline, and I'm not letting it sleep asynchronously. So you're not getting the LCD update very often. It basically has to finish a move. And yeah, there is some audio, but apparently it's not working. You can just imagine whirring. All right, so this is the other end. There we go. And you can see it moves and stops, moves and stops. So basically very quickly had something working with MicroPython. Yeah, now so my notes and observations. I had a really good experience with MP Remote. I've never used MIT from within MP Remote, but I had the Pico without the Wi-Fi specifically here. So I needed to install one of the packages. I think it was the AIO REPL. I wanted to try that out, and very quickly didn't have to work out any of the syntax. I could just type it in. I knew the MP Remote command, added MIP, MIP install, and then it just straight away install my package onto this micro. Very happy with that. I did try to use AIO REPL because I had half the code working in async I/O, and that was basically doing the display onto the screen. Unfortunately, what I was planning on doing was running the stepper code at the same time in the REPL, and of course, AIO REPL exists now. But in the 2 minutes that I sort of was trying to get this working, it didn't end up. I put all the commands in and it didn't work. So unfortunately, that's something to look into a bit further. But for me, it wasn't quite working. And from this whole project, the bottleneck was not MicroPython. It was not anything to do with the code, and it was a breeze to sort of put something together very quickly and just get something working. Next steps. I need to take the proof of concept and improve it. probably putting more files together and making an actual project of it. The keypad, as you saw, was not there and wasn't working yet. That shouldn't be too difficult to do. I need to have concurrency. I need to display the current location on the screen and also control the setting. Ideally through PIO, so that should be fairly straightforward. Generally, the CNC motion control systems use certain control loops. In this case, I'll probably use a velocity and position control loop to be able to ramp the motor up to a particular speed so it doesn't just stall. And then also a position control loop, so I can say go up 100 millimeters or 10 millimeters or 0.1 millimeter. That's the goal. Menu system would be good. PCB enclosure, all that boring stuff. And I should probably commit the project to Git because I'm currently just sitting there. All right, that's the end. Do we have any questions?
What are you using it for?
We've got some questions in there. What am I using it for?
Yeah.
The surface grinder.
Yeah.
It's a tool. I don't know. You use it.
Okay.
Yeah, it's a project. Yeah.
You always need new tools. I'm not going to argue with that. That's yep.
The grind surfaces.
Okay, Mike's got a suggestion.